This will be a brief introduction to the concept of our expanding universe. We're familiar that we live on a planet and our planet is orbiting our sun. That's a solar system, and that galaxies are just many solar systems mutually gravitationally bound to each other. Here's a drawing of our Milky Way galaxy. The core of the galaxy is in this location, and our solar system would be somewhere out here. Now, if we were to set up a camera on planet Earth and point it towards the core, you can take a picture like this. This is our Milky Way galaxy. So the band of stars we see in the night sky, these are all the stars in the disk region of the Milky Way, and we're looking towards the core here. Now, as you look towards the core, we have to look through a lot of gas and dust, and so in this picture over here, the dark regions here are blocking the light from stars behind it, and this would be dust and gas that is absorbing starlight, so we see these regions as dark. Sometimes when we're taking pictures of the Milky Way, one of our planets, one of our sister planets, will be captured in the picture as well. Like in this picture, we see the Milky Way here, and then down here we have Jupiter and Saturn. And you can almost see the plane of our solar system is tilted with respect to the plane of the Milky Way disk itself. Here we see a picture from Joshua Tree, and this little fuzzy thing in the early 1900s was called the Andromeda Nebula, and nobody knew how far away this object was. Today we know it to be the Andromeda Galaxy, called M31. Here's another picture using a wide-angle lens of the Andromeda Galaxy, but again in the 1900s they didn't know how far these celestial objects were. In the southern hemisphere we can see two more nebula, the Large and Small Magellanic Clouds. Here's our Milky Way as well. Here we see a close-up of these celestial objects. Again, scientists in the 1900s did not know how far away these objects were. Now in the 1900s, then scientists built a big telescope on top of Mount Wilson, and a famous astronomer, Edwin Hubble, used this telescope to try to answer the question, how far away were these nebula? Now here's the Andromeda Galaxy, a modern picture of it. What Hubble was looking for was a special kind of star called a Cepheid variable star. These are stars that go through a phase where they're dimmer, but then they get brighter, and then they get dimmer again and brighter in a regular period of time. Now other astronomers like Henrietta Leavitt had done research that led her to claim that by knowing the time period in which the star gets dim and bright, you can determine the star's intrinsic brightness, how bright it truly is. Well, if you know how bright the star is, and then you just compare that to how bright it appears in your telescope, you can then get an estimate of the distance to the star. So Hubble was very interested in these Cepheid variables because that would allow him to measure the distance to the Andromeda Galaxy itself. If the Cepheid variable was in the Andromeda Galaxy, then measuring its distance would also be measuring the distance to Andromeda. Here's his famous plate. Now it's a reverse image, so the core appears dark and the stars appear like dark spots. But up here in the top right, he makes a little mark here. In between those two marks is a star that is a variable star, VAR. He found himself a Cepheid variable. So all he had to do was to kind of measure the period of it getting brighter and dimmer, and then he would have a measure of its intrinsic brightness, and then he could measure the distance to that star and the galaxy. And his estimate was around 800,000 light years away. That the Andromeda Nebula was 800,000 light years away. Now that was a groundbreaking discovery because the Milky Way galaxy itself is around 100,000 light years across. So if the Milky Way is only 100,000 light years across the diameter of the disk, well, that must mean then that Andromeda was outside of our galaxy. So today, here's the kind of a layout of our local neighbors. We have the Milky Way here, we have the small and large Magellanic Cloud here, and here's Andromeda. Today we now know it's about 2.5 million light years away. It would take light 2.5 million years to get from our galaxy to the Andromeda, or vice versa. Now, using a photographic rig like this, you can take pictures of the Andromeda Galaxy. Here it's set up for observing the sun, but if you take this filter off and point it towards Andromeda, you get a picture like this. Now, normally you're taking long exposure pictures and then stacking them to reduce noise. But here it is, our Andromeda Galaxy. So Hubble estimated this thing to be 800,000 light years away, and he was off by some. We now know it's around 2.5 million light years away. But the point is that many of the other nebula in the 1900s that people had no idea how far away they were, Hubble and his team discovered that they were very far away indeed, and many of these nebulae were galaxies outside of our own galaxy. Today, with more modern telescopes like the James Webb Space Telescope, here's an example of what you can see in a tiny patch of the night sky. Thousands and thousands and thousands of galaxies. Now, Hubble didn't stop there, measuring the distance to these things. He could also measure the motion of these galaxies because of a property of light called the Doppler effect, and it applies to sound as well. We understand light to be an electromagnetic wave, and different wavelengths of the light appear to us as different colors in the visible spectrum. Now let's take this star here. Here's a star, and then here's our observer. If an object is stationary with respect to us, we will measure a certain combination of the colors of light from that object. But if the object is moving away from the observer, then that motion has an effect on the wavelengths of light. The wavelengths get stretched to the longer wavelengths, and that would be the red end of the visible spectrum. If the object is moving towards us, the waves in the light will get scrunched up. Smaller wavelengths appear blue to us. So if the object is moving away, the light will be red shifted. If the object is moving towards us, the light will be blue shifted. Now, of course, a galaxy is just a bunch of stars. So you can just measure the light from a galaxy and determine its redshift or blue shift. And if you know the amount of the redshift, you can then determine its velocity with respect to the observer. So Hubble not only could measure the distances to some of these nebulae like Andromeda, but he could also then measure the velocities of these other galaxies. And this is one of his famous results. It's a graph of distance on the x-axis and velocity on the y. And the little red dots would be different nebula, now understood to be galaxies. And so what you see is the line goes up and to the right, which means the farther the galaxy, the larger the redshift, so the faster the galaxy was moving away from us. So evidently, the galaxies in our universe were in motion, and there was a pattern to the motion. Nearby galaxies were moving away from us, but farther galaxies were moving away also at a faster rate. Let's take a look at us here. The black galaxy would be the Milky Way. Nearby galaxies would move a certain distance in a certain amount of time, but farther galaxies would move a greater distance in that amount of time. They were moving faster. Of course, this observation then cried out for an explanation. How to explain this pattern of motion of galaxies with respect to their distance to us? And the obvious candidate was that the entire universe was expanding. Space was expanding. So here we have our little circle getting bigger and bigger. This represents that all the space in the universe was expanding, so that any two galaxies over time, there would be more and more space being created between them. The galaxies would be moving apart. They'd be separating as the universe expanded. Let's take a look at these three dots representing three galaxies. Well, you notice they're far away here, but in the past they were closer together. So as space expanded in between them, the galaxies then are going to be farther away from each other. Notice also that there's no center point from which this expansion is happening. For observers in each galaxy, they will see the same thing. They will see all other galaxies moving away from them. There is no privileged position in the universe. Space is expanding everywhere, carrying galaxies farther and farther apart. This also explains then the mathematical relationship. So take the black galaxy here and the yellow one and the red one. So again, over time, the yellow galaxy is moving away from the black one, but the red galaxy is moving faster away from the black galaxy than the yellow galaxy. So the greater the distance between two galaxies, the faster they will be moving away from each other. One way to visualize this is with the balloon analogy. So here we have a balloon, and we've blown a little air into it, and then we keep on blowing air into it so the balloon gets bigger. So imagine all of three-dimensional space is the surface of the balloon. So that's kind of weird, but just the two-dimensional surface is three-dimensional space. So as the balloon is filled with air, all points on the surface move away from each other. And the greater the distance between 2 points, the faster they are moving away from each other. So this analogy is often used to capture what it means for the universe to be expanding. Space is expanding, and all the galaxies are being carried by that expanding space, and the relative motions of these galaxies will be away from each other. All galaxies will experience that kind of observation that all the other galaxies are moving away from them. Of course, this led to a big idea. Well, if the universe is expanding now, then in the past it was smaller. And then further back in time it was even smaller and smaller and smaller. And you get to some time in the past where the universe must have been in a very small volume. It was a hot, dense fog of energy. Everything in the known universe was in a tiny, tiny volume. And this led to the idea then of the Big Bang. So the Big Bang is a theory about how the universe evolved over time. And the earliest moment of expansion of the universe then would be the earliest stage of this Big Bang, as we call it today. Scientists estimated it was around 13.8 billion years ago that the universe started expanding from some tiny volume, and the universe was hot and dense, but then the universe expanded and it cooled over time, and fascinating things happened in the early universe that we can learn about in other lessons. But this introduces us then to the concept of the Big Bang. It naturally followed from the observation that our universe was expanding. And why did we think the universe was expanding? Because galaxies appeared to be moving away from each other. And there is a pattern to the motion. Nearby galaxies are moving away from us, but farther galaxies are moving away faster. And the way to model that would be that all of space is expanding. Our universe is expanding. The origin of that expansion and the history of our universe is the Big Bang theory of our universe.